Hello friends, today we are going to deal with the topic nanotechnology in textile finishing. What is this nanotechnology? Nanotechnology is all about making products from very small components to achieve improved properties and functionality. It is a technology that makes existing applications work more efficiently. It is gradually gaining global attention as it has vast potential in a broad range of end users. Nanotechnology has profit-making potential for the textile industry and is an upcoming technology in the area of textiles. Fabric finishing has taken new roots and has shown a great potential for significant improvements by application of nanotechnology. In this session, we are going to understand about nanotechnology, gain knowledge about the finishing agents used in nano finishing and its application, gain insight into the various nano finishes in textiles, learn about the characteristics of nano finishing. Nanotechnology is defined as the precise manipulation of individual atoms and molecules to create layer. Nanotechnology, according to the National Nanotechnology Initiative (NNI), is utilization of structures with at least one dimension of nanometer size for the construction of nanomaterials, devices or systems with novel or significantly improved properties due to their nano size. It is a field of applied science focused on the design, synthesis, characterization and application of materials and devices on the nanoscale. The term nano is a Greek word meaning dwarf. Nanotechnology is concerned with materials that are very small, that is 1 to 100 nanometer in length. 1 nanometer is 1 billionth of a meter or 10 to the power minus 9 meters. 1 nanometer is about 1 lakh times smaller than the diameter of a human hair. The basics of nanotechnology are that properties of substances significantly change when size is reduced to the nanometer range. When a large material is divided into small size particles in the nanometer range, the individual properties different from those of the large material. For example, ceramics have a property of brittleness, but if the grain size of the material is converted into nanoparticles, then the particles will be deformable. The use of nanotechnology in the textile industry has increased rapidly due to its exceptional and valuable properties. The chief areas of application of nanotechnology in textiles are nanofibers, nanotubes and nano finishing. In this module, we will be concentrating on nano finishing. What is nano finishing? Nano finishing is the application or coating of the surface of textiles with nanoparticles to create active surfaces with exceptional properties. The importance of nano finishing are: reducing the size of the particles to nanoscale primarily changes the properties of the material. The size of the particle plays a major role in determining their adhesion to the fibers. Largest particles agglomerates and will be easily removed from the fiber surface, while the smaller particles penetrate deeper and stick strongly into the fabric. The large surface area to volume ratio of nanoparticles makes it easy for them to attach to fiber or fabric. They have higher efficiency and durability due to the functions imparted by particles through the life of fabric. The nanotechnology based thin films and coatings are invisible and do not blur color and brightness of the textile substrate. The breathability and hand or feel of the textile is not affected by the coating of nanoparticles. Finishing agents. There are several nanoparticles. Zinc oxide, titanium dioxide and silver oxide are popularly used in nano finishing of textiles. Metal oxide nanoparticles are more preferable than nano silver because of cost considerations. Zinc oxide and titanium dioxide are non-toxic and chemically stable under exposure to high temperature and are capable of photocatalytic oxidation. The application of nanoparticles to textile material is aimed at producing finished fabrics with different functional performances. This table shows the various nanoparticles and the properties imparted. Titanium dioxide imparts antibacterial, UV blocking, self-cleaning, antistatic and wrinkle resistance. Zinc oxide imparts antibacterial, UV protection and antistatic. Silver, antibacterial property. Antimony pentoxide, flame retardancy. Clay, UV protection and flame retardancy. Tourmaline, which is a natural substance, fights odour. Magnesium oxide has self-sterilizing effect. Silicon dioxide and aluminum oxide has UV protection and water repellent finish. Fluorocarbon, water repellency. Next, let us see how the nanoparticles are prepared and applied. 6 methods commonly used to produce nanomaterials are plasma arcing, chemical vapor deposition, electrodeposition, salt gel synthesis, ball milling, and use of natural nanoparticles. Nanoparticles are applied on textiles by a 2-stage process. Primarily, it is a manufacture of new stable nanomaterial which must be protected against properties defined by the size of the particles. The second step is the creation of the foils, emulsions and dispersions that can be applied to the textile product. Nanoparticles are generally applied to textiles by coating using a composition of nanoparticles, a surfactant, ingredients and a carrier medium. The coating techniques include salt gel method could be an effective procedure to entrap organic and inorganic compounds with various functionalities on different surfaces. In conventional finishing techniques, pad dry cure, thermal radiation or chemical methods are generally employed to fix these nanoparticles on textiles. The process in such cases either involves several steps or is chemical intensive. The coatings produced are thick, unstable and do not allow the fabric to breathe properly. Recent studies show that LBL, that is layer by layer assembly, can produce ultra thin, transmissive and stable coating that is a chemically mild alternative to the conventional process. Layer by layer assembly method is a unique technique developed for production of thin composite films on solid surfaces. The process begins by charging a substrate appropriately, followed by immersion in an oppositely charged polyelectrolyte solution and then rinsing. The charged surface attracts the oppositely charged polyelectrolyte and binds it with the help of the strong electrostatic bonds. After rinsing, the substrate coated with a monolayer is treated with a solution of oppositely charged electrolyte solution. Repetition of this cycle can be used to deposit up to 20 ultra-thin layers. Application of nanotechnology in textile finishing. These are the different nano finishes imparted to textiles. Let's deal with each one in detail. Antimicrobial finish. Textile materials are a good media for growth of microorganisms. Nano-sized zinc oxide, titanium dioxide and silver have been used to impart antibacterial characteristics to the textile substrate. Metallic ions and metallic compounds exhibit specific level of sterilizing effect. The sterilizing effect is produced by the conversion of a part of the oxygen present in the air or water into active oxygen through catalysis with metallic ion and thus dissolves the organic substances. Also, the number of particles in unit area is increased by using nanoparticles, thereby maximizing the antibacterial effect. Silver ions have broad spectrum of antimicrobial activities. The method of producing durable silver containing antimicrobial finish is to encapsulate a silver compound or nanoparticle with a fiber reactive polymer like polystyrene co-malic anhydride. Nanosilver particles have a very large relative surface area, thereby increasing their contact area with bacteria or fungi and greatly improving their bactericidal and fungicidal effectiveness. Nanosilver is highly reactive with proteins. The cellular metabolism and growth of the microbes will be harshly affected when the nanosilver particles are in contact with them. It also suppresses respiration and transport of substances into the microbial cell membrane. The growth and development of the bacteria and fungi that cause infection, odor, itchiness and sores are restricted. Silver is a safer antimicrobial agent in comparison with some organic antimicrobial agents because of the risk of their harmful effects on the human body. Nanosilver particles have been applied on socks, healthcare products such as dressings for burns, skin donor and recipient sites to prevent the growth of bacteria. Titanium dioxide and zinc oxide are photocatalysts. Once it's illuminated by light with energy higher than its band gaps, the electrons in titanium dioxide will jump from the valence band to the conduction band, and the electron and electric hole pairs will form on the surface of the photocatalyst. The negative electrons and oxygen will combine into oxygen ions. The positive electric holes and water will generate hydroxyl radicals. Since both are unstable chemical substances, when the organic compounds falls on the surface of the photocatalyst, it will combine with oxygen ion and hydroxyl respectively and turn into carbon dioxide and water. This cascade reaction is called oxidation reduction. Through this reaction, the decomposition common organic matters in the air such as odor molecules, bacteria and viruses. It has been found that the photocatalytic activity of nano-titanium dioxide and zinc oxide could prove effective in protection against bacteria. Next is the antistatic effect. Synthetic fibers develop static charges since these fibers have very little capacity to absorb water. The antistatic properties could be imparted to synthetic fibers by the application of nano-sized titanium dioxide, zinc oxide whiskers, nano-antimony doped tin oxide and silane nanosol. The first three are electrically conductive in nature and are able to effectively eliminate the static charge that is accumulated on synthetic fabrics. On the other hand, silane nanosol improves antistatic properties as the silane gel particles on fiber absorb water and moisture in the air by amino and hydroxyl groups present in them. Wrinkle resistance is the next finish. In conventional finishing, wrinkle resistance is imparted usually using resins, but the application of resin results in decrease of tensile strength of fiber, water absorbency, abrasion resistance, dyeability and breathability. In order to overcome the setbacks of the conventional resin, nano-titanium dioxide and nano-silica has been developed so as to improve the wrinkle resistance of cotton and silk respectively. Nano-titanium dioxide has been used with carboxylic acid as a catalyst under UV radiation, which catalyze the cross-linking reactions between the cellulose molecule and acid. When nano-silica has been applied on silk using malic anhydride as catalyst, the wrinkle resistance has been efficiently improved. The fabric is treated with small particles of 10 nanometer in dimension. These tiny particles cross-link with cellulose to give desired amount of wrinkle resistance, and they cover the fabric so densely that it does not allow liquids to pass through it. But breathability of the fabric is practically unaltered. Water repellency. The water repellent property of fabric is improved through the creation of nano whiskers. These are hydrocarbons that are 1 by 1000 the size of a cotton fiber. They are added to the fabric to produce peach fuzz effect on the fabric without affecting its strength. The spaces between the whiskers in fabric are smaller than a drop of water, but it is larger than the water molecule. The water therefore remains above the whiskers and also above the fabric surface. However, it can pass through the fabric with applied pressure. The performance is permanent while maintaining breathability. Besides the nanotechs discussed above, another interesting development known as the nanosphere has been evolved to make water repellent fabrics. impregnation of nanosphere on the fabric is done using gel forming additives that repel water and avoid dirt particles getting attached on fabric surface. The mechanism is similar to that occurring in the lotus plant. The surface of the lotus plant is highly hydrophobic and has rough texture. When the water drops falls on the lotus leaf, they tend to form beads and will roll off even if the surface is slightly sloped. Thus, lotus leaf remains dry even during heavy rain. Moreover, the water drop gathers minute dirt particles as they roll, and hence the lotus plant leaves remain clean even during rainfall. Hydrophobic property could be imparted to a cotton fabric by coating it with a thin nanoparticulate plasma film. Fluorocarbon chemical was applied to deposit a nanoparticulate hydrophobic film onto a cotton fabric surface to improve its water repellent property. As the cotton fabric surface was rough, a high degree of phobicity has been attained while maintaining the softness and abrasion resistance. Self-cleaning fabric. There are basically two types of self-cleaning surfaces involving nanotechnology. In the first place, extremely water repellent, microscopically rough surfaces are created. Dirt particles can hardly get a hold on them and are therefore removed by rain or by simple wash in water. By using nano techniques, cloth is covered in a fuss of tiny whiskers which creates a cushion of air around the fiber. When water hits the fabric, it beads on the points of the whiskers. The beads compress the air in the cavities between the whiskers, creating extra buoyancy. In industrial terms, the material has been rendered super non-wettable or super hydrophobic. The whiskers also create lesser points of contact for dirt. When water is applied to dirty fabric, the dirt adheres to water much more than it adheres to the textile surface and is carried off with the water as it beads up and rolls off the surface of the fabric. Thus, the concept of soil cleaning is based on the leaves of the lotus plant. The second method is by photocatalytic layers. The titanium dioxide is a known catalytic compound. The fabric is treated with nanocrystalline titanium oxide to impart photocatalytic self-cleaning property. It shows its catalytic property by the absorption of a photon and jump to conduction band from the valence band, that is, able to remove the organic pollutants and xenobiotics from the textile material. We have already dealt with this in detail in antibacterial finish. Fouling organic material is destroyed by solar radiation. Superhydrophobic surfaces have water repellent properties. Surfaces with high contact angle also exhibit a self-cleaning effect. Water repellent hydrophobic surfaces can be produced using roughness of nanoparticles combined with hydrophobicity of polymer matrix. Attempts are made to incorporate hydrophobic composition such as organic silicon and organic fluorine into the synthesized material. Anti-pollen finish. This finish is achieved using a polymer like fluoroalkyl acrylate polymers which have antistatic or electroconductive composition. Nanoparticles of 30 nanometer size are applied onto the surface of yarns. The smoothness of the finish of the surface and antistatic effect does not let pollen or dust come close. It's used in coats, blousons, hats. Flame retardants they make it more difficult for fabrics to ignite and makes them burn slower and make fabric self-extinguish when the flame is removed. Flame retardants allow time to remove the clothing or put off the flames. Fire retardant coating is an advanced polymer-based nanotechnology that provides fire and flame protection to a broad range of materials without the risk of toxic byproducts during combustion. These protective coatings may be applied to metallic, ceramic, polymeric and composite structures using simple and low-cost coating techniques. Odor fighting finish. Tourmaline is a natural mineral which in contact with oxygen, carbon dioxide and water molecules in the air promotes electrolytic dissociation and emits negative ions. These fibers release undetectable negative ions and infrared rays that destroy odor-causing bacteria. The negative ions create a magnetic field that inhibits the reproduction of bacteria, thus eliminating odor and lowering the risk of skin infection or irritation. The characteristics of nano finishing of textiles are: nanoprotective layer is difficult to detect with the naked eye. Nanomaterials allow good ventilation and reduces moisture absorption, resulting in enhanced breathability while maintaining the good hand feel of ordinary material. Nano-processed products are toxic-free. This technology embraces environmental friendly properties. Fabrics stay bright, fresh-looking, and are more durable than ordinary materials. Nano-processed materials have protective coating, which is water and beverage repellent. Manufacturing cost is low, adding value to the products. When a substance is manipulated at sizes of approximately 100 nanometer, the structure of the processed cloth becomes more compressed. This makes clothing stain and dirt resistant. The crease resistant features keeps clothing neat. It saves time and laundering cost. To summarize, nanotechnology is a growing interdisciplinary technology, often seen as a new industrial revolution. The advent of nanotechnology has spurred significant developments and innovations in the field of textile technology. Nano finishes being developed for textile substrate are at their infantile stage, but appear to hold many promises in the varied fields of multifunctional applications. Nano finishing can replace the traditional finishing technique of textile products with products of superior quality and lower production cost. In future, one can expect to see many more developments in textiles based on nanotechnology. Definitely, these tiny particles are going to shape our future. Bye for now. Meet you in the next session. Thank you.